Corrosion Supervision 1. Hello everyone, welcome to video supervision number 1 on the corrosion course, in which I will show how to answer algebra questions on the thermodynamics and speed of electrochemical corrosion. Now, there is a question sheet for this supervision, and you can download the question sheet as well as my written solutions from a link which I will put in the video caption. You should be able to complete this question sheet using the content from the first 5 video lectures, and I do of course recommend that you read through the question sheet and attempt your own written answers before you look at my solutions or watch this video. That way, you can have the thrilling educational opportunity of working things out for yourself. It should probably only take you an hour or 2. Oh, by the way, I wrote a brand new question sheet for this video supervision, so the metals and the numbers here in this sheet are different from the ones in the question sheet that I distribute with the live lecture course. That means that if you are taking my actual course, you will not be able to use directly the numbers that you could copy from this video. But you will be able to use the same mathematical methods that we will look at. Now, just a side note, because I made a brand new example sheet and wrote new sample solutions, if there are any typos in them, I will put that in the comments below the video, and maybe you should check to see if other people have commented if there are any important typos. Hopefully there won't be, but it is a new document, so I will try and flag them up in the comments if there are any. Okay. Now let's go on to look at my corrosion questions, and as I'm going through them, I will talk about common mistakes which students have made in the past, and also the concepts which I most commonly have to explain or am asked to clarify in supervisions. Question number 1. The first part is just to make sure you can read cell notation. The second part is using the important energy-voltage relation between standard electrode potentials and standard Gibbs energy change. Pedants would say Gibbs function rather than Gibbs energy, but I say Gibbs energy change. The third part is using the Nernst equation to get electrode equilibrium potential at non-standard activity, which is usually the first thing you have to do in any electrochemical corrosion question. And the fourth and last part is doing some reasonably respectable algebra on the voltage drop which happens as a cell discharges when used as a battery. Part A, as I said, is trivial cell notation, which you should be able to read as magnesium metal dissolving at the anode and silver ions plating out at the cathode. There's a double vertical line or salt bridge between them. You just read that as a long tube, so that you don't have to worry about ions interfering with the other type of metal at the other side. The overall chemical reaction in the cell could therefore be written as equation A1, which is of course a displacement reaction. Remember, in the cell notation for a complete electrochemical cell, the process goes forwards by species moving from left to right, so that magnesium metal turns into magnesium ions. Then you imagine the magnesium ions filling up the solution and moving towards the right-hand side down the possibly imaginary tube. And then you can imagine them pushing the silver ions towards the right, and some silver ions are pushed onto the cathode where they plate out as silver metal. That's what's happening in part A. Part B asks you to use the data on standard equilibrium potentials given in the question to get the standard Gibbs energy change of the reaction in equation A1. Standard means unit activity, which in the questions in my course is the same as just 1 molar or 1 mole per decimeter cubed concentration for ions. So what you do is you take the energy-voltage relation from equation 2.26 in lecture handout 1, and you see that it says the delta G of reaction equals minus charge times reversible cell voltage, and at standard concentrations, equations 2.33 says that the reversible cell voltage is simply the cathode standard equilibrium potential minus the anode standard equilibrium potential. Putting values in from the data in the question, you get equation A3, and you see you evaluate a nice big positive cell potential of plus 3.162 volts. And you can note that in electrochemistry, having this positive cell potential is the criterion for a process that will go forwards. That's consistent with what you should absolutely expect, that this process will go forwards with magnesium dissolving at the anode and silver plating out. This is very thermodynamically favourable. In classic chemistry, we don't use this cell potential, we instead want to use delta G, and in equation A4 we evaluate delta G and we find there is a very large negative Gibbs energy change of reaction, which is minus 610 kilojoules per mole of magnesium. Now, please can you note how I have used the notation of volts and volts SHE in equation A3, because this is something students don't necessarily get right, and it would be better if they did. You see, what I have done correctly is to take the cathode potential written in volts SHE and subtract the anode potential, which is also written in volts SHE, and tell you the potential difference across the cell in just volts. This is correct, but obviously there are several ways which students write this down incorrectly in exams. But writing volts SHE and volts correctly, choosing to use the right one in each case, is important to get the concepts correct. The correct rule is basically that volts SHE behaves like the phrase height above sea level, whereas volts behaves like the phrase difference in height. If, for example, you have one individual mountain, you would have to talk about its height in meters above sea level, where the sea level is the reference which you measure from. If you have two mountains, you can subtract their respective heights above sea level to get the difference in height in just meters. Likewise, in equation A3, you see that the standard electrode potential of the cathode is correctly written in volts SHE because you need to write down the reference level, that's the SHE, or standard hydrogen electrode, from which this single electrode potential is measured, like the height of an individual mountain. Once you look at the difference between the two electrodes, you obviously should just talk about the potential difference in volts, because the difference between them is just a voltage, which has the same physical value regardless of whether you happened to measure both of them individually from the hydrogen electrode, or whether you measured both of them individually from some different reference value. The difference between them is just volts. So, do try to write volts SHE and volts correctly in exams using that guideline, because it means that you will correctly understand the concept of what's happening in this electrochemical thermodynamics. Part C asks for the reversible cell potential given the ions have non-standard concentrations, specifically 0.4 molar of magnesium 2+ ions and 0.2 molar of silver plus ions. You need to use equation A7, or 2.53 from the handout, which says the reversible cell potential is the equilibrium potential of the cathode minus the equilibrium potential of the anode. And each of those equilibrium potentials needs to be evaluated using the Nernst equation. For the magnesium dissolving to magnesium 2+ ions, the anode process, you can use the Nernst equation in A6 to find the actual equilibrium potential E subscript 0 at some general concentration. So the actual equilibrium potential is equal to the standard equilibrium potential at unit activity, that's the E superscript circle, plus a log term correction because of the actual concentration. So please pay attention that the Z in equation A6 has a value of 2, because 2 electrons are transferred from the magnesium in the bracketed term. Between the magnesium 2+, it loses 2 electrons to be produced from the metal. When you do the same for the silver ion to silver metal cathode in equation A5, you need to pay attention because the Z term there has a value of 1. That's because there's 1 electrode transferred between the silver metal and the silver ion in the bracketed log term in A5. If you wanted to make Z2, to make 2 electrons be the relevant value of Z for both equations A5 and A6, you might want to do that because it would make your algebraic life easier, but you would need then to use the silver plus activity squared in the log term of A5. Because to get Z equals 2 electrons, your reaction would need to have 2 silver ions reacting, and therefore the silver ion activity would appear twice in the log term, multiplied together, so it would be squared. Also, the silver metal activity would need to be squared because there would be 2 metal atoms plating out, but since the solid silver metal activity is 1 by convention, that won't affect the numerical result. Anyway, once you find the 2 electrode equilibrium potentials using the Nernst equation for each process, the reversible cell potential in equation A7 comes out as plus 3.132 volts, about 30 millivolts smaller than the value at standard concentrations found in part B. Now, in part D, we can use this for some respectable algebra. It asks in D if both the magnesium and silver electrodes have an area of 100 centimeters squared and are in 1 liter of solution, how much metal needs to react in terms of thickness of those metals so that the cell voltage, which changes when the ion concentrations change, drops by 1%. So first of all, note the nice numbers in this question. Because there is 1 liter of solution, if small x moles of magnesium dissolve, and hence 2x moles of silver plate out to balance the charge, the magnesium ion activity just becomes 0.4 plus x, as in equation A8, and the silver ion activity becomes 0.2 minus 2x, as in equation A9. The question asks about the cell voltage dropping by 1%. In other words, it needs to become 99% of the original 3.132 volts found in part C, so it needs to fall to about 3.101 volts. Now, if you take the expression for cell voltage from equations A5, 6, and 7, paying attention to where Z equals 1 and Z equals 2, then you get equation A10. The squared term in the log argument in A10 comes from paying attention to whether Z was 1 or 2. Or alternatively, you can get it by making sure you balance the equation like in A1. This gives you the quadratic equation for x that you need, and you can solve this to find one physically correct solution for the amount of moles of metal which reacts. Since you then have the metal surface areas, density and atomic weight, and you know how many moles of magnesium dissolve and silver plate out, you can then compute the thickness of magnesium which dissolves and of silver which plates out. Good. Oh, one last thing about question 1. The part D asks us to consider the new concentrations when the cell potential has changed by 1%. Of course, we know this is going to be a decrease to 3.101 volts from the original 3.132 volts, because Le Chatelier's principle says as the reaction proceeds towards equilibrium, the change in concentrations will oppose the driving force for the process. The driving force for the process is the positive reversible cell potential difference, the electromotive force it is providing. So of course this decreases from 3.132 volts down to just 99% of that. So that's what will happen spontaneously. That's why we're looking for an amount of magnesium dissolving and silver plating out. Question 2 asks you to find some of the equations for the phase boundary lines in a pH potential diagram for zinc, similar to the zinc diagram given in section 2.16 of handout 1, around page 23, with the difference being that in this question the boundary lines are for equilibrium between 100 micromolar dissolved zinc 2 plus ions or 10 to the minus 4 ion activity. In the notes, reproduced on the right-hand side of this slide, the diagram is for 1 micromolar. So the diagram from the notes here has a slightly bigger region for zinc ion stability where active corrosion is predicted to take place, because it is easier for the zinc to dissolve into more dilute solutions of its ions. Anyway, part A asks about the pure redox equilibrium between zinc metal and zinc 2 plus ions. So all we need is the Nernst equation, as in equation A 2.1, to give the equilibrium potential at non-standard ion activity, which in this case is 10 to the minus 4. If you plug in numbers for the ion activity, temperature is 298 kelvins, Z is 2 electrons per unit of this equation, then you should get an equilibrium potential of minus 0.878 volts SHE, which gives the correct position for the horizontal line where it should be on the pH potential diagram. And that is the answer as required in the question. Part B says, consider the line between the zinc metal immunity and the zinc hydroxide passivity regions. So show that this diagonal line obeys an equation which it gives in the question. Now, the equilibrium line here on the pH potential diagram is diagonal because it is both a redox and an acid-base reaction, so there is both electron transfer and proton transfer. That's okay, whatever. We can just use the Nernst equation, equation A 2.2. In this case, that's the Nernst equation in general. And if we do that, we can apply it to this particular process, this half reaction, as in equation A 2.3. The log term here can be greatly simplified, as the solids and the liquid H2O all have unit activity, and so only the term with the log of hydrogen ion activity matters, as shown in the simplified equation A 2.4. You can then draw on the definition of pH in equation A 2.5, so pH is minus log base 10 of hydrogen ion activity, and then you can simplify numbers and get equation A 2.7 for the diagonal line on the equilibrium phase diagram as required. Part C asks for the acid-base equilibrium line between solid zinc hydroxide and dissolved zinc ions. This is not a redox reaction, as the zinc atom stays in the +2 oxidation state. Because it's not redox, there is not an equilibrium potential, and you do not need to use the Nernst equation. In fact, you can't meaningfully use the Nernst equation. Instead, you need the conventional equilibrium reaction expression in equation A2.8, in which the equilibrium constant capital K is given in the data in the question. Solving as in equation A2.9, you can get the hydrogen ion activity at equilibrium, and then you get the pH of 7.43, using pH as minus log base 10 of hydrogen ion activity. And this is the equation for the vertical acid-base equilibrium line asked for in this part of the question. Okay. In the full diagram, there is another acid-base equilibrium under alkaline conditions between the passive solid zinc hydroxide, which is stable below a pH of around 11, and dissolved zincate ions, which are stable in more alkaline solution, giving active dissolution there. But this question sheet doesn't ask about that line. If it did, the maths would be similar to the maths in equation 2.9, A2.9 and A2.10. Good. Question 3 asks for short descriptions or explanations of electrochemistry, and I've tried to make my sample answer as painless and to the point and as easy to write down as possible. So, question 3a is, why is the ordering of metals in a galvanic series usually different from the order in the electrochemical series? This is a commonly asked question. The answer is that really these are two completely different things. So let's answer just by being precise about why. First, the position of a metal in the electrochemical series is determined by the standard electrode potential of its key oxidation reaction, like copper to copper 2+. That is a property of just one electrochemical half reaction, taking place at unit ion activities. The galvanic potential of the metal is the potential measured on the metal's surface under some conditions, like, for example, in neutral groundwater. This is the potential which is reached spontaneously when several half reactions take place on the metal's surface and they reach a pseudo-steady state, or they reach a steady rate process. This mixture of reactions achieves some charge balance, meaning no net accumulation or loss of free electrons, and it does so at the galvanic potential. At any other potential, there would be an imbalanced charge flow, and that would accumulate or remove free electrons in such a way that it would alter the surface potential towards the galvanic potential until this was reached. Now, since this galvanic potential must therefore be some sort of weighted average between the equilibrium potentials of all of the half reactions happening on the metal's surface, not just the metal dissolution half reaction, but also other reactions like oxygen reduction, and because the metal dissolution reaction generally is not, in fact almost never, at equilibrium with its own dissolved ions at unit activity, therefore the galvanic potential is rarely equal to the metal's standard electrode potential. It's a completely different thing. In particular, depending on what concentrations of chemicals are present in the environment and how good a catalyst the metal is for those chemicals' reactions, the galvanic potential might be close to the equilibrium potential for some other reaction, like the proton reaction, or it might, if it's completely inert for those, it might be closer to the equilibrium potential for the metal itself. But it is very unlikely to be at the same position as the metal's equilibrium potential. So, TLDR, standard electrode potential, is a thermodynamic property of the metal itself, and the galvanic potential is a measured property of several reactions taking place in an environment, and that mixture is unlikely to give you the same value as the standard electrode potential. Now, part B of question 3 is much more interesting. Why, it asks, does gold not normally corrode in even strong acid, but it does dissolve in a mixture of conch nitric plus hydrochloric acid? The key to answering this question is to remember we're in electrochemistry, and in electrochemical corrosion we predict whether a metal corrodes by looking at something like equation A3.1. We predict that a metal does corrode if equation A3.1 has a positive reversible cell potential with the metal of interest at the anode. For a gold anode with a standard electrode potential of plus 1.4 volts SHE, that's at the possible anode, there is no aqueous cathode reaction which comes anywhere close to making the expression in A3.1 positive. So definitely the most obvious cathode in strong acid, say sulfuric acid, is the protons, and they have a standard equilibrium potential of 0 volts SHE at pH 0. So the reversible cell potential here would be much less than 1, it would be minus 1.4 volts, and corrosion is predicted not to occur. That's true for unit activity, but minus 1.4 volts is so huge that even with extremely dilute gold ions, say picomolar or attomolar, the corrosion would still be predicted to not occur. Now, the mixture of conch nitric and hydrochloric acid is different in two ways. And these two ways are nice and obvious, provided you think of corrosion in terms of equation A3.1. So in order to have a positive reversible cell potential, you could either have a much higher cathode equilibrium potential or a much lower anode equilibrium potential. And in conch nitric plus hydrochloric acid, or aqua regia, we actually have both of those things happening. There's a high value of the cathode potential because nitrate ions are good oxidizing agents, and so you have your cathode reaction might be something like equation A3.3, where your nitrate gains electrons and is reduced, but this means it acts as an oxidizing agent for the gold, and it exerts a cathode equilibrium potential of perhaps plus 0.96 volts SHE. Meanwhile, the anode reaction is actually the formation of a gold chloride complex, AuCl4 1-, as in equation A3.2. So the complex is more stable than lone gold ions in solution, so its formation has a less positive equilibrium potential than the formation of gold 3+ ions. Now, these exact reactions are not examinable, but they might be something like the ones in A3.2 and A3.3. Taken together, you would end up with a small negative driving force if you considered the standard electrode potentials at unit ion activity, but it's close enough to 0 that given high nitrate concentration and or a dissolved gold concentration below, say, 0.1 molar, dissolution would be predicted to occur. So there's in this way you do expect gold to dissolve into the conch nitric plus hydrochloric acid. A couple of notes on this. There are several possibilities for the cathode reaction when nitrate ions are involved, and the equation I've written in A3.3 is just one of them. The second note is that you should come across at some point the story of a couple of Nobel Prize medals made from 23 karat gold being dissolved in acid. This was done deliberately back in 1940 in Denmark to prevent the gold from falling into the hands of the Nazis. So these were the medals of Max von Laue and James Frank, both of them political dissidents, and their medals were handed over to a sensible chemist, a Hungarian guy, I think, György de Hevesi, and he dissolved them in this mix of conch nitric and hydrochloric acid, and then the gold chloride stayed in solution quite happily for a few years, and much later it was reprecipitated and forged back into replacement medals. Part of this story, which I always notice is the comment from de Hevesy that this dissolution reaction, even though it's thermodynamically favourable, it's still pretty slow, and so he was quite concerned to make sure that it would actually be finished before anyone was to burst through the door and discover him trying to dissolve the gold. Okay. Question 4. The Faraday equation. Basically just for this purpose, importantly, you need to be able to convert current density in amps per meter squared into corrosion speed in millimeters per year, which is where you might most commonly find it given in those units, or microns per year for things which are less of a problem. So the question is, if you have a anode area of 20 centimeters squared, and you measure the corrosion current is 1 milliamp, calculate the current density and the mass wastage rate in kilograms per meter squared per year, and the corrosion rate in millimeters per year. Usually in one of my exam questions, the last part will be to convert between a current density that you've measured and one of the other units, which is a more useful way of writing down corrosion speed. And it asks you to do this if the metal is A, magnesium, or B, silver. Okay, and it gives you some data. And this is nice and easy to do. So you just say current density small I is current per unit area, or charge per unit area per unit time. So you just say equation A 4.1, the 1 milliamps in the 20 centimeter squared gives you 0.5 amps per meter squared dissolving metal current density. Then you use your Faraday law, as in equation A 4.2, or in the notes handout 1, this is around equation 3.3. Your current density, you have your relation ZF over A dN by dt for n moles, and you work out from that the by plugging in numbers, rearranging to get equation A 4.3, and then solve for the length which is lost dl in some time dt of 1 year, given this constant rate of dissolution. You should solve that and get that your magnesium is losing 1.14 millimeters per year, or if it was silver, 1.68 millimeters per year. Okay, questions 5 and 6 are very similar to each other because they're very important. There's two versions of the same sort of question. These questions ask you to calculate the speed of a spontaneous corrosion process in which the Tafel equation is describing the speed of each electrode half reaction. So question 5 says, cadmium experiences active corrosion in acidic solution according to the reaction a cadmium metal turns plus 2 protons gives you cadmium 2+, plus some hydrogen gas. It says, assuming that all the reagents have unit activity, the temperature is 298 kelvins, and that the rates of both oxidation and reduction half reactions are controlled by activation polarization, meaning the Tafel equation applies, calculate the corrosion potential E core and the rate of oxidation of cadmium in moles per centimeter squared per second. It also gives you some data. Now these questions can be solved in a standard way. Please do write down the principles which you're applying first, which are on this slide between equations A5.1 and A5.6, and then just solve algebraically. Principle number 1 in solving these speed of corrosion questions is always, first of all, the first thing you should do is to evaluate the actual equilibrium potential of the half reactions at the concentrations or ion activity relevant to this question. So that always means start by writing down the Nernst equation as equation A5.1 and A5.2, so that you find out the actual equilibrium potential for the cadmium electrode and for the hydrogen electrode in this question. You need to do this because equilibrium potential is what matters for doing kinetic calculations. In this question, the equilibrium potential is actually equal to the standard electrode potential because the correction term is 0, because in this special case, the the species have unit activity. But that's a very unusual special case, and even in this special case we still need to write down what the actual equilibrium potential is. It comes out as this minus 0.403 volts SHE for the cadmium, and 0 volts SHE, of course, for the protons. We need to write these down because that's what we're going to use. Do not just put standard electrode potential into the Tafel equation, because that will in general be wrong. So we need to, number one, always write down the equilibrium potentials, work out what they are in this particular question. The other principles are nice and straightforward. In equation A 5.3, we note that charge balance applies in spontaneous corrosion, so that's the anode current is equal to the cathode current. In fact, in this case, we have reaction on a single metal surface, so the area is the same for both processes, so the current densities are just straightforwardly the same. Principle 3 is that because we have a single metal surface, there must be some uniform surface potential, which we can call capital E. And principle 4 then, because we know the Tafel equation applies and describes the rate of both electrodes, we can put the information from the first three principles into the Tafel equation, and we can get equation A 5.6. And once we've written down those principles with some nice words of explanation, then we can just straightforwardly solve. We just need to do a bit of algebra. In general, you want to first of all solve to find E, the corrosion potential. You need to in this question because it asks you to find the value of E core, which is just E in my algebra. You solve for that first, as in equations to my equation A 5.10 in my answers. And once you've got the surface potential, then you plug that in and you evaluate the corrosion current density. Finally, in these questions, you convert corrosion current density into whatever units you get asked for to describe the corrosion speed. Often millimeters per year of the metal dissolving, or moles per centimeter squared per year of the metal which dissolves. Great. Question 6 is another speed of corrosion question like question 5. So it's going to again use the Tafel equation to get the speed of spontaneous dissolution, of this case, of a nickel anode. There are two differences. The first of all, the cathode reaction is in this case a copper cathode, so copper ions are plating out of solution onto some copper metal. And the second difference is that, like in most corrosion questions, we have non-unit ion activities, so 5 millimolar nickel 2+ ions in solution, and 250 millimolar copper 2+ ions. So that means that we can apply the same principles again, but if you forget to apply the correction in principle number 1, to which says always evaluate the actual equilibrium potentials in the question first, as the first thing you do. If you forget the log correction in the Nernst equation, you'll get answers which are quite significantly wrong. So you first of all apply the Nernst equation in equations A 6.1 and A 6.2 to find the actual equilibrium potentials for the two electrodes. And then we have principles 2, 3, and 4, that we have charge balance, again in this case in part A. This is for metals having the same surface area. In part B, it's for different surface areas, but in part A of this question, the areas cancel out, so we have an equal absolute value of current density for the anode and cathode. We have uniform surface potential because we are told that the solution has high conductivity, so there's no voltage losses. The only polarization terms are in the Tafel equation. We are also using the Tafel equation for both the anode nickel dissolution rate and the copper electroplating rate. If we're not told to do otherwise, then we should be using the Tafel equation to describe the speed of corrosion. It's only for cases like dissolved oxygen where you might have a system which is where it's important to know from memory that it's likely to be diffusion limited. In the case of these two metals, we're applying the Tafel equation, we're putting together these principles, and we're getting equation A 6.3, and then all we need to do is solve algebraically. So you go through some numbers and you solve first of all for the surface potential, and then to solve to get the current density for the nickel dissolution. You then translate your current density into whatever units you're asked for, in this case kilograms per meter squared per year. Most commonly in exam questions you'll be asked for millimeters per year, so you just need to use the conversion which is in question 4 of this example sheet. Part 6b asks you to do the same again, except now the area of exposed nickel is 75 times smaller than that of the copper. This you're doing to point out the importance of the area effect in corrosion. You're going to end up with a concentrated anode, so you solve by saying the anode and cathode have an equal absolute value of current, and therefore the current density for the nickel anode is 75 times bigger than the current density for the cathode in absolute terms, as in equation A 6.9. Then you solve this in much the same way that you solve the previous algebra. You just have an extra term of 1.88, which comes from the log base 10 of 75, which you will want to take at some point. Once you solve that equation, you get a slightly different surface potential of now plus 0.132 volts SHE, a slightly higher potential than was found before. Well, it's closer to the copper equilibrium potential because there's much more copper in this new system. And then plugging numbers in, you can find that the new rate of loss of nickel is about 6 kilograms per meter squared per year, much bigger than previously. It was about half a kilogram per meter squared per year. So that's, in terms of a corrosion rate or a speed in millimeters per year, that's greatly speeded up because you have a small anode and a large cathode. That's the area effect problem in corrosion, which we talked about in the course. And that's the reason why if you have bolts of a different metal to the sheet of metal that they're being used to attach to something, then you want to make sure that the bolts are not a more reactive metal, otherwise they can be destroyed very quickly. Okay, good. I think that's all of the algebra been through on this example sheet 1. If I get time or nice comments, then I will see you again for example sheet 2 in the future. So please do comment, rate and subscribe. Good.